Hello guys, in this video we are going to discuss the non-parametric techniques. So till now in our previous lectures what we have done is we have used the Bayesian classifier in the first place, then we used the k-means and the GMMs. So in the Bayesian classifier we had this rule or this formula. The formula says that your a posteriori will be equal to likelihood into prior upon evidence. So we ignore the evidence, and what we had assumed is we had assumed that this likelihood is of some distribution. So in our lectures we had seen that this was Gaussian. So we assumed our likelihood to be a Gaussian distribution, but that may not be the case every time. So this assumption of ours can be wrong, and if this assumption is wrong, the classification may lead to a bad or a wrong classification. So now what we are going to do is, what we did earlier was we used to assume that it is some distribution, say it is Gaussian, then we used to estimate the parameters. So then we saw the parameter estimation. So we saw the Bayesian parameter estimation, and we saw that any distribution needs some parameters. So like if you talk about the Gaussian, so the Gaussian has these two parameters, mu and sigma. So the mu and sigma will decide the whole distribution. So if we assume the likelihood to be a distribution, we just need to calculate its parameters and we are done. Hence that was a parametric estimation because we had to estimate just the parameters. So now what we are going to do is we are not going to assume any distribution. We are going to, so we'll not have any parameters over here, so hence the name non-parametric. So there are not going to be any parameters over here. So we are going to try to figure out the distribution of the likelihood from the data itself. So what we have is the data. So we have discussed this many times. See, in the training phase I have say many images of sunflower, say taking data as images. So and different classes, so this is a sunflower class, this is a rose class. So say consider I have many images of sunflower and I have to extract some feature from it. So say I am extracting the size of the sunflower, and what am I doing is I am plotting the size of every sunflower on this axis. So here let x be the size. So here x is the size. So for first image, say the size comes out to be 5, suppose. So it will come somewhere over here. For the next image it is some 4, so it is over here. So like this for many images I have just plotted the data over here. So now let us see what we can do with this particular thing. So now I'm not going to assume any standard distribution over here. So in that case, say suppose I divide this axis into some, what we say, bins. So this is a more statistical point of view where I am first discretizing my axis. So so this is like finding the histogram. So what this is a continuous data that I have. I am now discretizing it. I am making classes. Say this is class 1, this is class 2, class 3, class 4, class 5, class 6, class 7. Next what am I going to do is I'm seeing what samples lie in the classes. So here you can see there are no samples in class 1, so this will be 0. Here you can see that there are 2 samples. So so I'll give this some weight of say 2. So what it is going to be is the probability. So this is probability. So the probability of any sample lying in this range is 2 upon the total number of samples. That is quite intuitive. It is just probability. So I had these many samples. So it is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20. So I have 20 samples, and out of the 20 samples, 2 of them lie over here. So the probability is 2 on 20. Similarly, there are 1 2 3 4 5 samples over here. So the probability will be some 5 by 20. There are 2 samples over here again. So the probability is again 2 by 20. Now here 1 2 3 4 5. Here there are 5 samples. So again the probability is 5 by 20. So like this. So here again there are 2 samples, and here there are 4 samples. So this is what is the starting approach of a non-parametric technique. We are going to use these histograms now to guess the probability. So it is very important for non-parametric techniques to have large amount of data, because if suppose you have just less number of samples, say if suppose I just had one sample, or say 5 samples over here, so you would not get a good estimate. So your histogram would be very bad. So you need a good amount of data over here. So now what are we going to store? So now I have this particular thing. So I am just now storing the class, or say the class number. So I will store 2 and its probability. So say these are my classes 2 3 4 5 6 7. Oh, there is a 1 also. So there is a 1 also. So these are my classes, and I am going to store its corresponding probability. So there is a 0, there is a 2 by 20, 5 by 20, 2 by 20, and so on. So this is what I am going to store. Okay, so we were nice up till here. I hope this is clear to you. Now let us see what happens when we go to the 2-dimensional. So now what I'm going to do is I'm going to add another feature. Say let me add a new feature, that is luminance. So here I have considered the size. Now from this image I'm also going to extract what is the luminance, and we have discussed why do we go into the next dimension and all sorts of things. So now I have two features. X1 is size and x2 is luminance. So if suppose I had some training data, so with that I suppose got somewhat of this kind of plot. So here there is please remember, here x1 axis, here this axis is x1, that is the size, and this axis is luminance. So I have got this plot. So now you can see for the store. So here what I'll have to do is, so here you can see there were 1 2 3 4 5 6 7 classes. Hence I had to store all these 7 numbers. So I'll had to store 14 numbers, the 7 these and corresponding probabilities. So I have to store 14 numbers. But here you can see I don't just need to store these, but I need to store all of these also. So what I want to say is, now this single line over here becomes a box over here. So say consider this box. So here you can see I have so many boxes. So basically I have 49 boxes over here. It is 56 boxes. So here there are 7 and here there are 8. So I have 56 total boxes, and these boxes so because when you go into 2-dimensional you have 2 degree of freedom. So you can go over here also, you can go over here also. So you need to know the probability of one particular, so size is equal to 1 and luminance 1, size is equal to 1, luminance 2, size is equal to 1, luminance 3, and the story. So you have to store a great amount of data. So these many classes into 2, because into that many classes probability. So over here, how will you calculate the probability? It is the same. You say consider a box and you see how many samples fall into the box, and you, so here there are 1 2 3 4 5, and you divide it by total number of samples. So say total number of samples are n, so that is your probability. But you can see here the storage requirement went up exponentially. So similarly, if suppose I have 3 dimension, it will again multiply into 7 if I have more dimensions. And this 7 is also a very small number, because just for explanation I gave 7, but in reality this can be huge, quite huge. So this can be of size 100 or 200 of that sort. So, and then I can have dimensions also of the order say 10 or 20. So then the storage goes somewhat like this. So it is somewhat like this. So because of this, the histogram technique is not that useful, because it takes a huge amount of storage. So you can see that we did not have this problem in our Bayesian classifier, because in Bayesian classifier we had our formula and we just needed to save these parameters. So once we have the parameter, we know the distribution. That was the case. So because of that, we did not have that problem in our Bayesian or the parametric estimation. But over here in non-parametric, this is the problem that we face. So let us just modify this histogram technique a bit so that we can do something useful out of it. So let's see. So what we are going to do over here is, so let us come back to 1D. So I will also make this visualize in 2D in my next lecture. So yeah, so here let us assume that this is the same thing. So this is p of x given such. So now also, because I'm just going to talk about one class, I'm not going to talk about rows or some other class. So I have changed my notation from this to just small p of x. So because that is easy to write, that's it. So let us assume that this is some distribution, the true distribution. I don't know this distribution, I am just plotting this for some explanation. So this is unknown to us, this true distribution is unknown to us, and what we are going to do is we are going to approximate this distribution using some techniques. Okay, so what I'm going to do is, so here you can see what we did over here, the histogram technique. So let us see how we do this. Okay, so let us consider some region. So if suppose I want the probability of 4, so I want p of x is equal to 4. So I have this data, these samples are there with me, and I want to calculate what is the likelihood, that is what is the probability that given say it is a sunflower, what is the probability that the size will be 4. So instead of just saving all these so many probabilities, what we can do is we can save this data. So I am going to save this data that we have, and for say probability x is equal to 4, what I am going to do is I am going to have some region around this data. So we will talk about the region very nicely in our next lecture. So let this be any region. So let me say consider this is a region that I'm taking, this. So for 1D it will just going to be a line. So this is the region that I'm going to take. So actually its probability should have been this particular thing. the true. So this is the true distribution. So also please remember, I don't know this distribution. This distribution is unknown to you, unknown to us, unknown to me. So but I'm just going to for visualization I'm doing this so that you can understand what maths is going over here. So this is the actual probability of p of x is equal to 4 in this particular region. So I have taken this region. So now what I'm calculating is I'm calculating a capital P, which is we can say a smooth version of this probability, because I'm not calculating probability of x is equal to 4, but I'm calculating a range from 3 to 5, say, whatever. Now the assumption that we are going to make is this: we are since we don't know actually what this was, so we are going to make an assumption that the p of x is constant in this region. So here you can see that it is varying very highly, but what assumption that we are going to make is we are going to make that this is constant. So actually, so because I don't know what this distribution is, I don't know the function, so I cannot integrate this particular thing, because I don't know the function, I don't know what is p of x. So I assume that this is constant with respect to x. So this is something like this. And what this constant will be, we'll see, we'll come to that, what will be the constant. But let us assume that this is some constant, and if that is the case, if this is some constant, then I can take p of x outside the integral, because integration is with respect to x. So I can take p of x outside the integral, so it just becomes integration of dx. So that just means that I am going to take the integration of this particular region. So if this is some constant, so now what am I going to do is I am going to get this answer. So you can see that it is fairly okay kind of approximation, because you can see that the error is over here and this much is the error. So let me denote it like this. So this you can see is the error, so which is quite okay, because we don't know, and we'll see how can we reduce this also. So this is something that I'm going to do. So this is the maths that is with it. So I can just denote this thing, because this thing will be a constant, because this is a constant. So this is like an area of a rectangle. So the area of a rectangle will be given by this region, which I am denoting as V, because in higher dimensions it will become volume. So this is just 1D for just a simple explanation, but in higher dimensions for 2D, 3D, 4D, 5D, hyper volume and all those of all those things will come. So just for notation sake I have done this V, and this is P of x. Now what is the value of this P? We can approximate the value of this P as what we did before. So I can see how many samples are there in this particular region, say 1 2 3 4. So there are 4 samples on this region upon the total number of samples. So I can say that the probability of this region is 4 by n. So that is the thing that we borrowed from our histogram technique. So that is why I explained you this. So we came from here to here. So we can use this thing. So I can say that this capital P is nothing but k by n. So what is k? K is number of samples in the region. So here you can see that there are 4 samples, 1 2 3 4. So k becomes 4 over here, and total number of samples n. So we get our equation k by n is equal to this p of x into v. Now from here we still don't know what is this constant that we have, so that is what we have to figure out. So p of x is that constant. So p of x can be approximated as k by n upon v. So we got the value of this constant to be k by n upon v, where k are the number of samples inside the region, n are the total number of samples, and v is the volume of this particular region. So in 1D volume does not make sense, but for higher dimensional volume makes sense. So it is just the integration of the region, that's it. So this is the first step towards the non-parametric techniques. So that was good for an introduction. So we'll continue in the next class from here. Thank you so much for watching. Thank you.